Bones can be classified in a number of ways. On a macroscopic level, they can be classified according to their shape. So we have long bones, such as the bones of the arms and the legs. We have short bones, such as some of the bones in the fingers and the toes, such as the carpals and the phalanges. Flat bones, such as the bones of the skull, or irregular shaped bones, such as the bones of the vertebrae. Also, on a macroscopic level, bones can be divided into two classes, compact bone or spongy bone. And if one cuts a long bone in half, such as is shown here, one can easily see the difference between compact bone and spongy bone. Compact bone lines or covers the outside of the long bones, and that looks pretty much solid without many holes or gaps. In other words, it's compact, whereas the bone that fills the inside of the long bone is composed of thousands of spicules or trabeculae interconnected like a sponge. In other words, it is spongy. And the reason for this is very obvious if you think about it. If the entire bone was made up of compact bone, it would be much heavier. And additionally, the spongy bone is where hemopoiesis occurs, where blood cell formation is carried on. On the microscopic level, bone is classified as either woven, which is primary bone or immature bone, or lamella. Woven bone occurs wherever there is a need for bone in a hurry. It is a temporary expedient, formed in a relatively sloppy manner, such as in the fetus, in the developing bones of the skull, in healing fractures, etc. It contains much more ground substance, so that it stains very basophilically with H&E. It contains less collagen and much more coarsely interlaced collagen, and it has lots of osteocytes, which we'll look at in a little bit, randomly scattered in its matrix. And woven bone is pretty much always replaced by the second type of bone, which is lamellar bone, except in a very few places in the body, where the flat bones of the skull interdigitate, in the tooth sockets, and in the insertion of some tendons into bones. Lamellar bone, by contrast, is formed more slowly and carefully by the successive layering of lamellae of fine type 1 collagen fibers, highly ordered in a parallel fashion with more collagen and less ground substance, so that with H&E, as shown here, it stains eosinophilically. Lamellar bone is not formed de novo. Woven bone is always the first bone that is formed, and then by various methods, which we'll look at later, it is replaced by lamellar bone. There are 4 different cell types associated with bone formation and resorption. The first of these is the osteoprogenitor cell, which is derived from mesenchyme. And osteoprogenitor cells give rise to osteoblasts, which are the bone-forming cells. As these osteoblasts secrete the precursor of bone, osteoid, which is transformed into mineralized bone, they get trapped in it and they become osteocytes, which have an important role in maintaining the matrix of bone tissue. And the 4th type of cell is the osteoclast, which is the bone resorbing cell, the bone dissolving cell, which functions under various conditions of bone remodeling or calcium need, which we'll look at a bit later. Osteoblasts are responsible for the synthesis of the organic components of bone, such as type 1 collagen, the glycosaminoglycans, and glycoproteins, and they're also responsible for the later deposition of the inorganic components of bone. And collagen comprises 90% of the organic matrix. Osteoblasts synthesize the precursor of bone called osteoid, and then this osteoid is converted by mineralization, which is also carried out by the osteoblasts, into bone. An important point for you to remember is that in contrast to cartilage, bone formation always takes place appositionally. That is, new bone is deposited on the surface of old bone. As the osteoblasts secrete osteoid, they become trapped in it, and eventually they are trapped in the mineralized bone and are then known as osteocytes. And osteocytes, like chondrocytes, are not just passive cells, they're actually very active cells. The osteoblasts, as they are secreting osteoid, are joined to one another by fine cytoplasmic extensions, and these extensions are maintained once the osteoblasts are trapped, and these extensions, these cytoplasmic extensions, pass through thin channels in the bone called canaliculi. And these osteocytes, as I think I started to say, are responsible for maintaining the health of the bone. If the bone is broken, the osteocytes will die, or if, conversely, if the osteocytes die, the bone around those osteocytes will also die. The osteocytes maintain connection to blood vessels in the periosteum and also to blood vessels which pass through the bone and derive nutrition from these blood vessels in order to maintain the health of the bone. Osteoclasts are bone resorbing cells. They are part of the mononuclear phagocyte system, and they are derived from monocytes from the blood. They secrete lactic acid, citric acid, and proteolytic enzymes and proteoglycan degrading enzymes that attack the bone matrix and dissolve the calcified ground substance. When osteoclasts need to dissolve bone, as they do particularly to woven bone, they sit on the surface of the bone, make specialized contacts with the bone, and start to dissolve the bone, forming a little lacuna called a Howship's lacuna directly under the cell. Once that Howship's lacuna has formed, enough bone has been dissolved, the osteoclast will move on somewhere else, and this Howship's lacuna will then be filled in with lamellar bone formed by the osteoblasts. It's through the combined action of osteoclasts dissolving bone and osteoblasts synthesizing new bone that bone is constantly remodeled throughout life. This slide, I think, nicely shows osteocytes in their lacunae and the canaliculi, which pass from osteocyte or from lacuna to lacuna, and as well as passing to the surface of the bone here, where they would derive nutrition from the periosteum, which, as you can see, has been removed during decalcification. This diagram shows the formation of woven bone, probably in the fetal skull, with osteoblasts sitting on the surface of the bone, secreting osteoid, becoming trapped in the bone, mineralizing it, and forming this fairly disorganized woven bone. The osteoid, which is synthesized, shown here, is pre-bone, as I've mentioned, and it now has to be mineralized. Mineralization, or calcification is another word for it, involves the formation within the matrix of crystallites of hydroxyapatite, and you don't need to remember that complex formula of hydroxyapatite. The osteoblasts are responsible for mineralizing the osteoid, and they secrete these matrix vesicles, which contain alkaline phosphatase and other enzymes and are loaded with calcium and phosphate ions. These matrix vesicles rupture, resulting in an increase in the local concentration of calcium and phosphate sufficient to initiate mineralization. So these small centers of mineralization in zone B here grow, and eventually they fuse with one another, and so mineralization spreads as these foci of mineralization grow bigger and bigger until it spreads across the entire bone. This is shown in this electron micrograph here. Here is zone B, where mineralization is just starting. This is zone C, where these matrix vesicles are starting to fuse with one another. They continue to fuse, and the area of mineralization continues to grow along these collagen fibers, seen here, until the entire bone becomes mineralized. So you should really understand this process of mineralization. New bone can be formed in two different ways, as it says here. By intramembranous ossification, in which there's de novo bone synthesis, such as the flat bones of the skull, and endochondral ossification, which requires a pre-existing cartilage model, and is the way that the large weight-bearing bones are formed during embryogenesis and maturation of the bone. In intramembranous ossification occurs within an area of very well vascularized mesenchymal tissue, and no cartilage is required. What happens is these mesenchymal cells differentiate into osteoprogenitor cells, which then differentiate into osteoblasts, and these osteoblasts start to lay down a little bit of osteoid. As the spicules of osteoid thicken, as shown here, the osteoblasts become trapped, become osteocytes as they are trapped in the matrix, and then the matrix becomes mineralized, as we've talked about previously. This woven bone will eventually be remodeled by the action of osteoclasts chewing away this disorganized bone, osteoblasts coming and sitting within the Howship's lacunae and laying down new lamellar bone. In areas of the bone, such as the skull, such as the vertebrae, such as the ribs, which are destined to persist as spongy bone, and in which there will be a marrow cavity, the plates of bone are penetrated by blood vessels, giving rise to bone marrow cells. And of course, don't forget that all bone is surrounded by a periosteum on the outside and usually not very visible endosteum on the inside. This somewhat out of focus, I'm sorry, picture shows a spicule of woven bone, very disorganized osteocytes being remodeled by osteoclasts. Here, new bone is being laid down on this side by these osteoblasts, and eventually these osteoblasts will also sit on this side of the bone and fill in these Howship's lacunae with lamellar bone.